Welcome back to the Deep Dive, where we process the latest research and engineering documentation, distilling it into the knowledge you need to navigate the modern tech landscape.
Today we are doing a really substantial deep dive into the evolution of Java.
That's right. We're focusing specifically on the landmark features of Java 21 and, the continuous stream of changes we're seeing in all the recent releases.
And this isn't just a list of new methods or something. It's more like a reimagining of the platform. We're looking at paradigm shifts that fundamentally change how you build highly concurrent, high-performance applications.
Right. And our goal here for you is to extract the core insights. We want to show how these changes from massive scalability tools all the way to syntactic clarity empower a modern developer.
Exactly. Maybe someone like Syed, a developer building scalable microservices in a high-demand environment. How can they write code that is genuinely better, faster, and, importantly, more maintainable?
That's the mission. To get beyond the marketing bullet points and really understand the mechanical why behind these updates. So, we've already established modern Java is an architectural powerhouse. So let's start with the one feature that's generated the most buzz in the last few years. The foundational shift in how Java handles threads. Okay, let's unpack Project Loom.
Virtual threads. They are, without a doubt, the single biggest game changer.
Okay.
For decades, Java concurrency was all about platform threads, which are basically just heavy wrappers around operating system threads.
And they were expensive, very resource intensive.
So expensive, they had huge stack footprints, and crucially, they blocked the OS when they were waiting for I/O operations. So if you needed thousands of concurrent connections, well, you'd run out of resources very quickly.
And that's what forced developers into those really complex, non-blocking programming models.
Exactly. Futures, callbacks.
Reactive streams, all that stuff, just to handle scale.
Precisely. And virtual threads, which came out of Project Loom, they just eliminate that headache. They're incredibly lightweight, managed entirely by the JVM, and they let Java go back to that simple, intuitive model of one thread per request.
So where's the magic? How does that work?
The magic is that the JVM can manage literally millions of these threads. It parks them cheaply when they hit a blocking I/O call, and then it remounts them onto a small pool of what are called carrier platform threads when the work can resume.
That sounds almost too good to be true. If I'm a developer like Syed and I can suddenly spin up millions of these threads, doesn't that just create a debugging nightmare?
That is the critical follow-up question.
How do you maintain sanity with that kind of scale?
Right. And the answer is that massive scale requires massive discipline. And that discipline is imposed by structured concurrency, which arrives shortly after virtual threads.
So that's the organizational framework.
That's the framework.
Tell us what that framework does exactly.
It makes sure that all the concurrent tasks you launch within a specific block of code are treated as a single unit of work. So if you start several child tasks, the parent scope can only complete once all of its children have finished.
Either successfully or by failing.
Exactly. It creates this really predictable flow. It simplifies error handling, cancellation, all of that task lifecycle management. If one child task fails, the whole scope can be shut down cleanly and predictably.
So no more thread leaks, no more orphan tasks running forever in the background?
Gone. It turns what used to be asynchronous complexity into something that looks and feels like simple synchronous code.
Okay, so Loom lets you scale astronomically, and structured concurrency keeps it all manageable. But for this to work, the JVM itself, the core engine, has to be seriously fast.
Absolutely. And the foundation has been radically hardened. We should talk about garbage collection, which, used to be a major source of latency.
It was the Achilles heel for a long time.
For a long time, yes. But modern JVMs running generational ZGC, or the enhanced G1 collector, have achieved ultra-low pause times. We're often talking sub-millisecond ranges, even on massive heaps.
Why is that generational part so key? What's the insight there?
The insight is that most objects you allocate, they die young. They don't live very long.
Right.
By introducing generations, the GC can sweep that young generation very frequently and very cheaply. So most short-lived objects, like temporary objects from a web request, get cleaned up without ever triggering a much more expensive full heap collection.
And that's what gives you that predictable low latency performance that's so essential for, what, high-frequency trading or low-latency APIs?
Exactly, those kinds of systems.
Okay, that handles runtime performance, but what about startup time? In a cloud or microservices world, startup is almost as important, and Java, well, it had a reputation there.
a deserved reputation, historically. But that's been largely mitigated now, primarily through something called class data sharing, or CDS.
How does that work?
Well, imagine, in a microservice environment, you might have 20 identical instances of your application running. CDS lets the JVM pre-process and share all that internal class metadata across those running JVMs.
So instead of every single instance loading and parsing all the standard library classes on its own.
They just point to a pre-warmed snapshot. It cuts out a massive amount of redundant initialization work. And when you combine CDS with the continuous improvements to the JIT compiler, Java is now genuinely competitive on startup speed.
Okay, so if that was all about the architectural engine, let's move to the driver's seat, the daily coding experience. This is where things get cleaner and more expressive for the developer, right?
This is where you really feel a difference day to day. And we have to talk about pattern matching.
Which goes way beyond a simple instance of check now.
Oh, way beyond. It's now integrated into switch expressions, and most importantly, it supports record patterns.
Give us a concrete example. How do record patterns make life easier?
Okay, imagine you have a shape interface. It's implemented by a record called rectangle that holds a length and width.
Okay.
Before, you'd get a shape object. You'd have to check a shape instance of a rectangle. Then you'd manually cast it to a rectangle, and then you could access its components.
A lot of boilerplate.
So much. Now, with record patterns, you can write a switch that matches the type and deconstructs it in the same line. You just write case rectangle, int length, int width.
And that automatically pulls the data into local variables. So you're cutting out, what, 3 or 4 lines of casting and temporary variables?
At least. And it's type safe. It's exhaustive. And when you combine it with sealed classes, the compiler can actually warn you. It can say, hey, you handled the rectangle and circle, but you forgot about triangle.
Let's touch on those 2 building blocks then, records and sealed classes. Records are for immutable data carriers. What makes them so much better than just a plain old Java class?
It's the guarantee of conciseness and immutability. A record defines the state, and that's it. It just eliminates all that boilerplate, the constructor, the accessors, equals hash code, toString.
All the stuff your IDE writes for you anyway.
Exactly. It just distracts from the actual data modeling. Yeah. Records handle that 90% case of simple data transfer beautifully.
And sealed classes are the other side of that coin. They define the boundaries.
They're the necessary partner. Sealed classes let you express a domain model where you know all the possible subtypes at compile time. You restrict inheritance.
So you could have a user action sealed interface.
And you could explicitly name the only 5 valid implementations. That architectural control is massive. It prevents future developers from accidentally extending the hierarchy in ways you never intended. It leads to much stronger, more predictable code.
Okay, moving on to readability. Let's talk about text. String concatenation has always been one of Java's ugly spots.
It's been pretty messy, yeah. Especially with complex multi-line strings with variables inside.
But now we have string templates.
Finally, this gives developers a really clean, intuitive way to interpolate variables directly inside a string. So instead of all those plus signs.
Hello plus user.getName plus...
All right, you can just use str. Hello, user.getName.
You're
balanced.
That's a huge win for clarity. And I've heard that if you use a specific template processor, like for SQL or JSON, it can actually improve safety.
It can. It can help prevent common injection attacks by automatically escaping the data as it's inserted. It's both cleaner and potentially safer, which is a rare combination.
So before we move on, let's circle back to concurrency safety for a second. We've got millions of virtual threads. What about safely sharing data in that environment? What replaces the old problematic thread local?
Thread local, the source of so many memory leaks.
The pain of cleanup, especially in a pooled environment.
Well, the official successor is scoped values. They're designed for passing data down a thread hierarchy, but without all the baggage. They're immutable, and they're only readable within the scope where they're bound.
So if a request starts, I bind a transaction ID to a scoped value. Every subsequent method call or child thread forked within that block can read that ID.
But they can't change it. And you don't have to worry about that value leaking into the next request that gets handled by the same carrier thread.
It just simplifies context management immensely.
Completely. It's a type-safe, performant way to share context that fits perfectly with the structured nature of modern Java concurrency.
That's a fantastic transition, because now we're going to look outward. Java isn't just improving internally, it's also breaking down barriers to other high-performance ecosystems.
Right, specifically the native world. And this is where Project Panama is delivering huge results. The key component is the Foreign Function in Memory API, or FFM API.
Which is the replacement for the notoriously painful Java native interface, JNI.
Painful is a good word for it. JNI was complex. It required writing C header files, dealing with manual memory management. It was incredibly error-prone.
So what does the FFM API change for a developer who just needs to call a C library?
It standardizes and simplifies that interaction using pure Java. It provides a type-safe, structured way to interact with functions outside the JVM. You can allocate and manipulate native memory off-heap, bypassing the GC, and call native functions directly.
All without writing any of that JNI boilerplate.
Zero.
Why is this so important for Java's future?
Because the highest performance domains, we're talking machine learning, big data analytics, cryptography, they often rely on highly optimized C and C++ libraries. By making that integration efficient and safe, Java hugely expands its reach into these specialized areas.
It makes it competitive for tasks that were previously dominated by Python or C++.
Exactly.
Speaking of hardware optimization, what about getting the most out of the CPU itself?
That's the domain of the vector API. We're talking about SIMD, single instruction, multiple data operations.
Right.
Most modern CPUs have these specialized registers that can process, say, an array of 4 integers in a single clock cycle instead of one by one. That's vectorization.
So the vector API lets Java code explicitly access that parallelism instead of just hoping the JIT compiler spots the opportunity.
Correct. It exposes these hardware capabilities safely through a Java API. This is invaluable for developers in scientific or financial modeling who are doing large-scale array processing. The throughput gains are massive.
Okay, we've covered scale, complexity, and performance. Let's finish up with something simpler but still important: accessibility. Onboarding new developers.
Yes, and this is where unnamed classes and instance main methods address that traditional hello world problem.
The classic boilerplate of public static void main string args.
Right. Every tiny Java program needed a full class wrapper. It was a hurdle for beginners and just slowed down quick scripting.
And now, if I just want to write a quick utility, I can just write the code and the JVM understands how to run it.
Exactly. You can write much leaner, top-level code. It feels much more like a modern scripting language for small tasks, making the learning curve shallower and prototyping much, much faster.
Okay, so let's synthesize this. When you look at the total impact, what does it all mean? We have the revolution of virtual threads, the elegance of pattern matching, the power of the FFM API.
The cumulative effect is profound. This is Java shedding its old image as a slow, verbose, overly complex language. It is now explicitly engineered for 3 key modern demands.
Which are?
Hyperscalability through Loom, domain modeling clarity through records and sealed classes, and high-performance native integration through Project Panama.
So for a developer like Syed, it means less time battling frameworks and boilerplate.
In airtime, focusing on delivering actual business value with expressive, robust, and lightning-fast code.
It really sounds like the platform itself is actively steering developers toward cleaner, more robust engineering.
It is, and the pace of innovation is only getting faster. And I think the final thought for you, the listener, is not to treat these major versions as just a set of completed features.
Yeah, that's interesting.
The Java ecosystem is now heavily using preview features to gather feedback and continuously improve. So to stay on the cutting edge, you need to explore those preview features, things like advanced stream collectors, enhanced exception handling, deeper JVM tuning options. Engaging with these developments now is how you ensure your applications are truly future-ready.